Welcome back. So today the lesson is we're going to use the principle of calculus and derivatives to study the derivatives of specifically the inverse of the trigonometric functions. Now in the previous lesson or two, one of the ways we showed how to write the inverse of a function was to start with the function we're trying to write the inverse of. And in this case, we're trying to write the inverse of the sine function. And the one way you can write the inverse of a function is actually just to swap the y and x variables. So the implicit form of the inverse of the sine function would be the equation x equals the sine of y. And we're actually going to apply our derivative to this. Okay, so we're going to be differentiating both sides of this equation. I'm going to put my derivative operation on both sides. And on the left side, we have a derivative of x, which is 1. And on the right side, we have an implicit derivative. If the sine of y, the derivative would be cosine of y times the derivative of y. And now our goal is to find y prime, noting that that would represent the derivative of the inverse of the sine function. And so I'm going to divide both sides by the cosine of y and arrive at y prime is the cosine 1 over the cosine of y. Now I'd like to improve on this by trying to express this derivative in terms of x. So to do this, I am going to draw on some prior knowledge. In your pre-calculus or trig class, one of the key trigonometric identities was this one. We've mentioned it a couple of times this year too. But if the variable were to be y, sine squared plus cosine squared equals 1. And I'm going to come up with an expression for cosine of y in this one. By solving for cosine of y, I would get cosine squared is 1 minus sine squared. And then, since this is really the cosine of y squared, cosine of y would be the square root of 1 minus sine squared y. And so I could take this and plop it in over here, but the expression would still be in terms of y. So I would like to improve on this one further. And remember that the original equation we started with was x equals the sine of y. So this quantity down here, where I've got sine squared y, or that's really the sine of y squared, this is really now just x squared. And so I can rewrite this further as cosine of y is the square root of 1 minus x squared. And that's how I'm going to write my derivative. 1 over the square root of 1 minus x squared. And so this really is the derivative of the inverse of the sine function. Now, some textbooks some people refer to the inverse of the sine function as the arcsine function. And so in your notes or on your list of derivatives, you have it written as the derivative of arcsine of x. That's just a synonym for the derivative of the inverse sine function. And so this is the way we're going to write it on our paper, on our list, and use it. Is the derivative of the inverse sine function is 1 over the square root of 1 minus x squared. For the other two, I'm not going to spend as much time proving what the derivatives are, especially for our cosine, since it's very similar. So it turns out that this one, and I'm just going to write the conclusion this time, the derivative of the arc cosine function, also called the inverse cosine function, the derivative actually is just the negative of the previous one. So there's really not a whole lot to say about that one. We could prove it very much the same way. Essentially, the negative sign comes from the fact that the derivative of cosine has a negative in it. Okay, but the proof would be very similar otherwise. So we can write this one down too, and I'll spend a little more time with the derivative of the inverse tangent function. So here we wish to prove what the derivative of the inverse tangent function is. And we're actually going to start with the implicit form of that, and that is taking the equation y equals tangent x and instead writing it as x equals tangent y. So now this is the implicit form of the inverse tangent function. And we're going to take a derivative again of both sides. So I'm going to put my derivative operation on both sides. And it means I have to know the derivative of x, which is 1. And the derivative of the tangent function, we know, is secant squared. But this is an implicit derivative. It's tangent of y, so we must multiply by y prime. And so by solving for y prime, I'll have an expression for the derivative of the inverse tangent function. And I'm going to get y prime is equal to 1 over secant squared of y. Now for this one, again, I want the derivative to be expressed in terms of x, not y. And so again, I'm going to rely on a trigonometric identity. Now in the previous proof for the inverse sine and cosine, we relied on this trig identity here. Sine squared y plus cosine squared y equals 1. Now this time our derivative does not contain a sine or a cosine, it contains secant. So there's another trig identity that is similar to this one. In fact, I can find it just by dividing every term in this trig identity by cosine y. So think about dividing sine squared by cosine squared. That would make tangent squared. And if I divided cosine squared by cosine squared, that would be 1. And if I divided 1 by cosine squared, I would get secant squared. And so I now have an expression for secant squared that is 1 plus tangent squared y. Now this would still involve y. However, the tangent function was the thing I was working on in the first place, and in our initial statement, the tangent of y was equal to x. And so since tangent y equals x, I could change this equation to secant of y equals 1 plus x squared. And that is what I'm going to be putting in my derivative over here. So in place of secant squared, I'm going to be writing 1 plus x squared. And so now this is the way we're going to write our derivative. And this is the derivative of the arctangent function or the inverse tangent function, however you wish to write it. Okay, so some people write arctan x, but that's a synonym for the inverse tangent function. And we've proven that that derivative is simply 1 over 1 plus x squared. So our next slide has these derivatives and a few other ones, but we're mainly interested in the inverses of the sine, cosine, and tangent. Now, the previous proofs showed the basic rule, but these are all written as if we're going to plan to use the chain rule. So they're written instead, the derivatives of arc sine of u, arc cosine of u, and arc tangent of u, and they follow the basic principle that we just proved, other than they all involve the derivative of u. Okay, like we're going to use the chain rule. We always end up multiplying by u prime. So the basic rule for derivative of arc sine x was 1 over the square root of 1 minus x squared. This one now accounts for, it might not be inverse sine x, it might be inverse sine of 5x or inverse sine of x squared, in which case we have that as being u, and then we must multiply the basic rule by u prime. And so all three of these now are written in terms of the chain rule. And that's the way we're going to be demonstrating the use of them today. So here I've got an inverse sine function, but it's not inverse sine of x, it's inverse sine of x squared. So to make use of the chain rule, let's substitute u for the inner expression, x squared, and then we're going to use that differentiation rule that the derivative of arc sine u is simply u prime over the square root of 1 minus u squared. So maybe we know our u is x squared, and we could make a note also that in this case u prime will be the derivative of x squared, which is 2x. So to write the derivative, all I've got to do is fill in this template, 2x in place of u prime, and then x squared in place of u, and this becomes 1 minus x squared, and let's just simplify the parentheses out a little bit further. It'll be the square root of 1 minus x to the fourth, and that is my derivative. Our other example here will be an inverse tangent function. It's not inverse tangent of x though, it's inverse tangent of 3x. And so we'll use the chain rule and let u equal 3x. And at the same time, we'll just make a note that u prime, the derivative of that, will be 3. And so this is going to be really thought of as the arctangent or inverse tangent of u. And so then our derivative will follow the template that we learned earlier, u prime over 1 plus u squared. And we're just going to fill this in. So u prime will be a 3, and u is 3x, so this will be 1 plus the quantity, 3x squared. And so finally, let's just simplify the parentheses. My derivative will be 3 over the 1 plus 9x squared.